the main message is actually that detailed understanding of routenates, as was presented now by Anna a few minutes ago, is actually made possible by two things. First, there was a development of computational techniques that made it possible, but there was also a paradigm shift in understanding of the problematics. And to tell that, the way I will do it, I will actually do a bit historical presentation of the subject. So how things were before the subject was understood. So most of my talk will be about older work, and only part of it will be about some recent results. So, yeah, the people, I mean, given that I will cover a set of papers, there are many people that were involved in this. I guess the person who was on most of the papers is Antoine. There were collaborations also with the people listed there, notably by Luca de Medici, and more recently with Rok Žitko and Alan Horvath from Ljubljana. Yes, so given that the technologies that I will use, I mean, the theoretical technique approach is the DMFT, but I will actually, so I want to say in advance that I will be combining results on few different specific problems. I will discuss the model results, which will be the DMFT on semicircular, on beta lattice, that is semicircular density of states, free orbital problem. I will discuss LDA plus DMFT results on strontium-2 ruthenium-4, but I will also discuss just the solution of the impurity model, which is the problem one solves in the DMFT, but without self-consistency, so for featureless flat hybridization. Yeah, and the Hamiltonian that describes the situation is the Kanamori Hamiltonian. So one has the band part and the interaction that is described as, that has part that describes repulsion between particles. And then there is a Hund's rule coupling that lowers the energy, the local atomic energy of the spin, and or the orbital momentum are large. So yeah, the outline of the talk is this. So I will start from this historical point of view, how puzzling the routenates appeared 10 years ago. Then I will describe so the DMFT results on strontium-2 ruthenium-4 and on the model. I will introduce the Janus physics. So then I will discuss in more detail the impurity insights. So the fact that there is a separation of spin and orbital scales. I will discuss the spectral fingerprints of the Hund's metals. And finally, I will briefly discuss the non-firm liquid behavior. This will be elaborated in much more detail by Jan in the next talk. So let's start. So one way to look at the problematics is by comparing the behavior of 3D oxides versus 4D oxides. So in 3D oxides, one has more narrower orbitals, narrower bands. The interactions are bigger, and the physics one understood at the time was that the correlations are signified by in photon emission as by quasi-particle peak and Hubbard band. So here is the data on calcium vanadium free, and then there is also onset of oxygen states at lower energy. On the other hand, in routenates, one did not see the lower Hubbard band. So there is just quasi-particle peak and then the onset of oxygen states. And hence, there were people that found that the LDA actually describes the photon emission well. They wrote that there are no strong correlations in routenates. On the other hand, as Anna already told, so one sees strong correlations. First, there are large mass enhancements. There is very low coherence scale. There is bad metal behavior. So for instance, if you compare here the resistivity of routenates, one sees Fermi liquid behavior only below 20 Kelvin, whereas in vanadates, one sees the Fermi liquid behavior up to much higher temperature. Invariant S1 also has smaller mass enhancement, yet larger U over W ratio. Okay, so also other routinates have remarkable behavior, several remarkable properties, very low coherence scales, lowest one in calcium ruthenium 3 below 2 Kelvin, and calcium ruthenium 3 furthermore has a bizarre behavior of optics with square root 1 over square root of omega non-Drude behavior. So, for instance, now I will quote several citations from the old literature that will demonstrate the level of understanding. First one is from the experimental paper. So they ask, so they very intelligently ask what causes the exposed disposal of a low coherence scale with great insight. So then, presently we know how to explain this. So the coherence scale is low due to the Hund's rule coupling. But I also quote now some wrong statements in the theoretical literature at the time, well, by some people that are also in the audience, but also some other people. And this is not to say bad things about anyone, but rather just to illustrate that there was something qualitative to be learned. So first, there is an old LDA plus DMFT paper on strontium to ruthenium 4. They used quite large interaction parameters, and they did the simulation at temperature 1000 Kelvin. And they argue that the temperature seems to be high, but it's actually quite sufficiently low because this is smaller than the lowest atomic excitations and the characteristic low energy scale. And the characteristic low energy scale they have in mind is the width of the quasi-particle peak. So that was, of course, completely wrong because the coherence scale is not, in Hund's metals, is not given simply by the width of the quasi-particle peak. Of course, at the time, the techniques, numerical techniques were not ready even to address this question. This was only made possible by technical developments in which also some people in the audience played a key role. So this hybridization expansion continuous time Monte Carlo solvers enable reaching low enough temperatures these problematics to be addressed. And one of the pioneering papers on this is the paper by Philip and co-workers on the spin freezing transition. So what they found is that, so this is now the calculation for the semicircular density of states free orbital problem. And one sees that as one changes the filling from towards the Hall filling, they found rapid change of behavior from a Fermi liquid to a frozen moment. That is a situation where the susceptibility goes like local moment light, so 1 over temperature. And they also found that on the point where this is changed, there is a apparent power law behavior of self-energy. And they, I mean, whereas their study certainly is pioneering, they also in the conclusions, for instance, say that they interpreted this as evidence for a t equals 0 transition. So they didn't expect that the coherence scale could be very low. Well, they say that it could be, but they, I guess, don't believe quite that. Another paper, which is by also other important people that made that contributed majorly then to understanding of the Hund's metal, was the paper on pnictides by Christian and Gabi. So initially they pictured those compounds as being very close to the Mott transition, which was also then later corrected. So certainly I think this illustrates that a different way of looking at all this was needed. And this was the physics of J, of Hund's coupling. So I guess the first paper that looked at this more carefully was this New Journal of Physics by Christian and Gabi. This clearly demonstrated that as one increases Hund's rule coupling, the coherence scale progressively drops, and one sees the Pauli behavior of susceptibility in increasingly lower temperatures. And so this paper appeared about simultaneously on arXiv. So these were independent works, and they are like first important works on the Hund's metals. So what about routines? Now I will go to my work. So we looked at strontium-2 ruthenium-4 at the time. The band structure is shown here. There is a wide XY band and more narrow XZ, YZ bands. We use T2G orbitals when it functions so narrow energy window. We calculated interaction parameters, and we use hybridization expansion Monte Carlo to solve this. Quantity we calculated is the quasi-particle scattering rate. So, and here it's plotted divided by temperature. So when this is gamma over T is linear, this indicates Fermi liquid behavior, sorry. So this picture illustrates the crossover from a coherent behavior at low temperature to an incoherent behavior at a higher temperature. One can identify the coherence scale, the two coherence temperatures for the different orbitals from that. And here then in this table, we documented how these are changed as a function of J. One sees that as J is increased, the coherence scales drops dramatically, and the masses increase to the ones that are consistent with the quantum oscillations and specific heat. And what is important is that in all the consequent work that looked at several experimental properties, including the one that was earlier presented by Anna, used these same interaction parameters and essentially the calculation within the same framework. So we calculated several experimental observables and compared them to experiments, night shift, so 1 over T1T, photo emission. All these quantities show first good quantitative agreement with experiments, and they show occurrence of a low coherence scale. And this all breaks down if J is not there. Okay, so now I go to, how am I doing with time actually?
I think you 10 minutes. You should ask.
Okay, so I will now discuss the model work. So more the physics of Hund's coupling in more detail. How does this work? So there are actually two aspects that are important. One aspect is already that I mentioned. So there is certainly suppression of the coherence scale, but another part of the physics is that actually the effective interaction depends on the effective interaction that determines where the transition to the multi-insulating state takes place also depends on J. And the way it works is that away from Hall filling, the J leads to suppression of the effective interaction. That is, you move electrons around, and you you need to pay some repulsion, but you are paid by formation of the large spin state, which leads then to lowering of the interaction and effective repulsion. The situation is opposite at Hall filling, where you need to, whereby moving an electron around, you also lower the spin. So this then costs extra energy. In the paper we had by with Luca and Antoine, we put these things together. And so here, what is plotted is the quasi-particle weight as a function of interaction parameters. And one sees that first, if one looks at where the Z goes to 0, so where the multi-insulator transition takes place, one sees that this is being pushed to larger values away from Hall filling by the Hund's coupling. And the opposite happens at Hall filling. Now there is another effect, this suppression of the coherence scale, that is manifested by suppression of Z for the case of 2 electrons in T2G, for 2 electrons, but not for the case of 1 electron. And hence, one can also look at this contour map where we looked at a set of fillings and set of interactions, fixing J over U to 0.15, I guess. And one sees that there is at 2 electrons and 4 electrons, one sees that the correlations are strong far away from the mode state. So why such a behavior? One fruitful line of thinking about this that is pushed forward, especially by Luca, is by considering the so n equal 2 or n equal 4 state as being influenced by Hall-field mode state. So by considering this as a Hall-field mode insulator. I will not discuss actually these results more. I will discuss another aspect that is, I guess, equally fruitful, but it's also, in the end, it's a manifestation of the same physics. So now the understanding I will describe from that is has been reached by considering the impurity problem. So the atom, so the problem with atom coupled to a buff, multi-orbital problem, but without self-consistency. I mean, not necessarily. And this has been done first by Christian and Gabi. And so what one does is one starts from the impurity problem, so described by Kanamori interaction, and one does the Schrieffer-Wolff transformation to a Kondo problem. So the Kondo problem that one gets involves spin degrees of freedom and orbital degrees of freedom. Now, if one has the interaction described by the Kanamori interaction that has also this L-squared term, the impurity Hamiltonian looks like that. It involves also some quadrupolar terms. It has SO free symmetry. Whereas if one does it, if one changes the interaction by omitting the L-squared term, the symmetry is higher. So one has full SU free orbital symmetry. There, in this case, the notation is easier. So there are a bit less terms. But all this distinction actually is not qualitatively important. Because, I mean, this we demonstrated in a paper together with Roque, that in an RG sense, the distinction between these two models becomes irrelevant at low energies.
Jernej?
So
This is
yes,
your 5 minutes.
I have 5 minutes. That's great. So now why okay, one thing that one sees when one does this Schrieffer-Wolff transformation is that the spin coupling is suppressed very strongly. So why is that? Why does this occur? One can understand this quite easily. So by considering that if by this pictorial, so if here I have 2 electrons, they have parallel spins, and fluctuations to Hall-field state occur when they occur. It's beneficial that the buff had parallel spin to the atom, so that this excited state has lower energy because it has parallel spins. So this is basically the mechanism that explains the suppression of the coherence scale in Hund's metals. And you see again that that there is this physics of being influenced by the Hall-field state. Well, yeah, one can calculate these Kondo coupling constants, and so the red are the orbital coupling constants, the blue are the spin orbit coupling constants. On x-axis parameter that determines whether one prefers the fluctuations to n equal 3 states, that's on the right, or to n equal 1 states, that's on the left. And one sees that when the fluctuations to these n equal 3 states, the spin Kondo coupling constants drops. And so, okay, now this is a result of an energy actually on a Kanamori Hamiltonian, and what is plotted is the susceptibility times temperature. So that is the local moment, spin moment, and the orbital moment. And one sees that as one cools down, first the orbital moment is suppressed and then quenched, and then the spin moment. So that's the physics of that. With now I will return to strontium 2 ruthenium 4. One sees this behavior also in LDA plus DMFT calculations. So the spin susceptibility red behaves local moment like when the orbital susceptibility is already let's say Pauli like temperature independent. It's also nice to look at this. So here is a calculation of the entropy So as the entropy is, as the temperature is lowered, one first quenches the orbital moments and then only later spins. So these two, now I will discuss spectroscopic signatures of that. So the fact that one has two-stage screening has consequences, and the consequence is that the quasi-particle peak has structure. So here is a calculation where one, for semicircular density of states, taking different values of J over U and adjusting U such that one always has the same renormalization. One sees that when J is 0, the quasi-particle peak has no particular shape, but then as you increase J, there is a side shoulder that develops. This calculation here is done at 2 electrons. One could think that this perhaps signifies some atomic multiplet splitting. To demonstrate that this is not the case, I show here now the calculation for different values of interaction. Here, this only now this is done at 4 electrons, so this shoulder now happens at the unoccupied side, as is also characteristic for rutinates. And here I increase interaction, and by increasing interaction, I see that the feature moves inwards. So hence, because if it moves inwards, means it's not atomic multiplet, because the Baire scale increases. So it's really shape of the quasi-particle peak. I don't have time to go into this, but this was actually indirectly already measured in optical experiments by Dirk van der Marel. I mean, seen in the, so here we compared the LDA plus DMFT results on optical conductivity, and we were able to pinpoint the spectral weight at about 0.2 eV or so. So there is excess spectral rate, weight that you can only interpret in terms of the presence of this side hump. Yeah. Okay, so now this is, I think, one of the last slides. So now there have been recent work, both by us in Ljubljana and by especially by Gabi and Jan van Delft. So this will be given more in the next talk. However, so this was now the intention of that work from our side was to try understanding this incoherent regime, partially incoherent regime, better. So it turns that when you start from the Anderson like problem, the orbital and spin scales are perhaps factor 10 or 20 apart, but never further. However, when one has a Kondo problem, one can independently tune the parameter, and this happens because of these mixed terms that mix the spin and orbital degrees of freedom. However, if one can, in a Kondo model, one can suppress those terms, and when one does that, one sees here is energy calculation on such a problem. So the blue line is starting from a Kondo problem that has parameters obtained from the Schrieffer-Wörth transformation. That is the ones corresponding to an Anderson Hamiltonian. Then, yes?
We're out of time.
Okay, it's last, I will finish in a minute. So as the mixed terms are being suppressed, one sees the appearance of a plateau. This plateau has, so the entropy there has a value that can be interpreted in terms of the overscreened two-channel SU3 fixed point. Why two-channel SU3? So the Hamiltonian one, one has essentially is a Hamiltonian that involves local orbital moment coupled to buff orbital moment. They are both described by SU3. And then one has two channels corresponding to spin up and down. And then this has consequences so by this, one can get the value of the residual entropy in this regime. And there are also consequences for the frequency dependencies of the susceptibilities. I guess this will be covered by Jan next. So let me skip that. And well, if I'm out of time, then I will just simply thank you for your attention.
All right. Thank you very much. Are there any questions locally with you, Jernej? Questions in the room. You're not going to just come up here. Too. All right. Otherwise, we have one here locally from UNOChem. Into this microphone here, like right here. Just ask.
This.
Yeah, that's the microphone.
Oh, okay. Hi. About the ruthenites being well described as Hund's metal, what is the direct experimental signature that speaks to importance of Hund's coupling?
I would say that, well, I mean, indirect is that if you do the calculations without the spin orbit coupling, all the detailed quantitative agreement on several properties simply is unable to reach that. A quite direct evidence, I would say, is actually the optical data I was describing here. So the blue symbols are calculation. The thin wiggly line is the measurement, and the detailed agreement, especially this about 0.2 eV regime, is, I would say, I mean, it's indirect because it's optical, but otherwise it actually directly points to the existence of this side peak, and that's the spectroscopical evidence for Hund's metal.
So then, do I understand it correctly? When you try to do calculations within DMFT formalism, if you don't take Hund's coupling into account, you don't get good agreement in optical conductivity. You take
nothing, not just optical conductivity.
Okay.
Everything will break. So one aspect that you certainly don't get is, so in quantum oscillations, one is known, and also in ARPES, one sees that the XY sheet is heavier than the XZ, YZ, so the alpha and beta sheets, so the gamma Fermi surface sheet is heavier, and this you don't get if you don't take the Hund's rule coupling into account. If you would keep Hund's rule coupling to 0 and just increase Coulomb interaction, you would need to increase it to a non-physically large value. So this is 5 eV, which is unphysically large for a 4D oxide. And even if you do that, you would get that the mass enhancement for the alpha, beta, and gamma sheet are practically equal, which is experimentally not the case.
I believe we have a comment by Antoine here. Do you have a mic, Antoine, or do you want to type? I guess that means typing.
No, Antoine, but come here.
Okay. Yeah, I just wanted to, can you hear me now?
Yes.
Yes.
I just wanted to add one comment in relation to Una's question, which is that indeed, as when it comes to the actual order of magnitude of the Hund's coupling for this class of materials, there was a clever photoemission experiment by Johann Chang in Zurich, who exploited the existence of two different final states in photoemission, so that by taking the difference into these two between these two final states, a direct quantitative value of the Hund's coupling could be extracted. This was done for calcium ruthenium 04, but the insulator member of that family, and the value that comes out is about 0.3 eV, which is precisely the value which is necessary to get all these nice agreements on many different quantities from the calculations that Jernej presented.
Can you do the same with strontium ruthenate? Because calcium ruthenate and strontium ruthenate are quite different. They are similar, but also different, right?
They are very, very different. They are very, very different materials, but
right.
Their band structure is different, but you would not expect their interaction strength locally to be very different. And in fact, constrained RPA calculations for both materials give very similar value of U and J.
Mm-hmm. Right.
Oh, okay. So thank you very much. I'd like to keep this a little bit on time. So let's thank Jernej again.
Thank you.